This pattern has been used to detect fraud across the world, from an individual's financial data to the revenue sheets of billion-dollar corporations. But the equation that dictates this pattern is surprisingly simple, and perhaps more strangely, it appears everywhere in nature, from mathematical constants to the surface areas of rivers. So how does it work? Well, it all starts with a simple question. Suppose you take a data set which has a range of different magnitudes, let's say the populations of countries around the world. Now let's focus on the first digits of these numbers. As the list extends on, we get more and more data about these first digits. The question is, will certain digits be more common than others in terms of how frequently they appear as the first digit? Should we expect it to be evenly distributed across each digit, or will there be some sort of pattern? As you may have figured out from the intro, the distribution actually looks like this. The first person to figure out this pattern was Simon Newcomb, an astronomer and mathematician. In 1881, while he was looking through a book of logarithmic tables, a sort of table which could perform calculations, he noticed something that other people may consider a coincidence. The pages closer to the beginning of the book were significantly dirtier than later pages, so they must have been used more. In other words, numbers which start with 1, or smaller integers in general, occur more often than large ones in nature, since these numbers were being used more for calculations. This eventually led him to find this distribution. But how did he determine these values? Let's first consider a number n. No matter what m is, it can be expressed like this. As you can see, a controls the first digit of number n, and k controls the magnitude. Now the probability of n having the first digit d is given by the probability that a is in the interval d to d plus 1. Now, we take logs of both sides of the expression for n and use the product rule. You may be wondering what is the need for this, but it will be important later. Next, we also take logs of the interval we need, giving us this expression. So this is what we need to find out. So how do we do it? Newcomb first proposed that all natural numbers could be expressed as ratios. Many numbers are given in units, so the resulting number is a ratio of one measurement to another. For example, the number given for a car's mass could be the ratio of its measured mass to 1 kilogram. As a result, taking logs means the logarithm of a natural number is just a result of summing logarithms of other numbers. Newcomb then proposed a different concept. Let's say you have some decimals distributed on a circle of circumference 1 according to their magnitude. Now let's create another circle dedicated to the sums of the points. For example, let's say I take a point on the left circle and add its magnitude to another point on the same circle mod 1. Then it will be plotted on the other circle. We can repeat this with more numbers. As this process continues, the distribution of the sums becomes uniform. But what does this and the idea of ratios mean? Well, going back to the car example, we have a sum of some logarithms. But we could also say the mass is density times volume, so we get more sums. We can also say that volume is length times width times height, giving us even more sums. This could continue on even more, so what we get is many different logs being summed together. Remember that every logarithm of a number can be expressed like this, so each of these logarithms can be expressed as the decimal part log a plus its magnitude k. So what we are effectively doing is summing up different log a's and summing k. But remember, log a, which comes from this sum, must be a decimal since a is between 1 and 10, so log a is between 0 and 1. So to make it a decimal, we apply mod 1 to the sum, meaning we only take the decimal part and add the integer part of the sum onto k. So since we are summing decimals mod 1, the sums become evenly distributed, so log a is evenly distributed between 0 and 1. And since it is evenly distributed, the probability of log a being in this subinterval is just the length of the subinterval divided by the length of the entire interval of 0 to 1. That gives us our final equation for the probability. This is why we took logs of n, so that we could use the fact that log a is distributed uniformly. But although this proof was published in 1881, it wasn't well known until physicist Frank Benford noticed the same phenomenon in 1938. He compiled over 20,000 different numbers together from many different datasets, and what he found was the same distribution of first digits. In light of this evidence, the pattern became known as Benford's law. Later in the 1990s, mathematician Ted Hill provided what is considered the definitive proof of the law, which clarified under what conditions the law must hold. First, the dataset must span many orders of magnitude. And second, it must be scale invariant, so changing between units does not alter the distribution of first digits. Additionally, two types of datasets often follow the law. One is multiplicative data. Since there are many multiplications, we get many log sums, which means that log A will be uniform. The other is a dataset which comes from mixing many different distributions together, resulting in a dataset which follows the law. So how does the equation detect fraud? Well, let's say a company alters its revenue to inflate its profits. They would choose larger numbers and use more 9s and 8s to make profits look larger. But this would result in a first-digit pattern, which strays from Benford's law. Take Enron's financial data as an example, a company caught for fraud. In general, when financial data does not follow the expected distribution, fraud is a possible reason. So, although Benford's law is mainly known for its role in fraud detection, its real beauty comes from how this simple mathematical rule arises in unrelated datasets in the natural world. And as such, it is yet another example of how mathematics describes the world around us.